సార్ కొంచెం అది చేసి సార్ మళ్ళీ కొంచెం ఇబ్బందిగా ఉంది మాకు అది. ఇప్పుడు మళ్ళీ వాళ్ళకి 11:10కి బ్రేక్ ఉంటుంది. మరి బ్రేక్ ఇచ్చింటారా ఎంసీఏ వాళ్ళు?
LSTMs, which is basically management without the information or decides how much of the long-term memory to be continued to the next layer or discarded to the next level, and also how much of the short-term memory to be added to the long-term memory, right? Using 3 gates. Alright. So GRU, gated recurrent unit, is also based on the same concept. Okay, but it is less complex than the LSTM cells. It is less complex than LSTM cells. In LSTM cells we have 3 gates, here we have only 2 gates. Okay, there we maintain 2 lines. One is the long-term memory and the short-term memory. Alright, here we only maintain 1. That itself adds or discards are, adds some new information to the long-term memory. Right? So that means there are update and reset gates. So the update gate helps the model to determine how much of the past information need to be passed along the future. That means this is like a forget gate. In your LSTM cell, it is like a forget gate. Okay, the same functionality is also same. Right? So you take this sigmoid, alright? So this gives the values in the range of 0 to 1. And the reset gate uses model to describe how much of the past information to forget. Okay? So here, how much of the past information to be passed, here, how much of the past information to be forget. Okay? So these are the 2 gates, 2 sigmas. If you notice here, there is one sigma here, there is another sigma here. Alright? The computation is similar. Finally, it combines both like this. Alright? So it computes both, it gives ZT weightage to HT minus 1 and 1 is ZT weightage to HT. Alright? So I am not spending much time on this because it's similar to this. Once you understand LSTM cell, if you go through this one more time, you will understand it. But the only thing that you need to remember is that there you are taking 3 inputs, giving 2 outputs. LSTM. Here taking 2 inputs, giving 1 output. Right? It means you don't have 2 separate long short-term memories. The best thing is encoded in the same line. That is in the GR. Then you have 3 gates. Here you have 2 gates inside GR itself. Alright. But the concept is same. Concept is to discard unnecessary information and filter out the necessary information. Right? That's the concept of both LSTM and GR. But GRU is less complex than the LSTM cell. Alright, because there is less computation here inside the GRU cell. Now I got the transformer models. So your attention is required here. Oh God, this is not a dull list. Is it for me only or do you also did not? I'm just telling you. Is it? Okay, my research section. Okay, let me explain. These are very big networks. Actually, your speech has to be big. There is no way that I can do this. There are 2 parts in the transformer. One is the encoder, this entire thing is the encoder, and this entire thing is the decoder. Okay. The attention mechanism that we use in transformers is the core part of many of the large language models. Okay. Large language models like BERT, GPT-3, GPT-4, all this based on the attention mechanism. Okay. It is very much important for you to understand the attention mechanism. How much of the transformer you will understand? It's a different thing. To understand attention mechanism, what is happening inside the attention mechanism. Okay. So we'll go one step at a time. So if you look at this transformer model, the basic transformer model, this is the input, and you are producing the embedding and then doing the positional encoding. And then it is passed through a stack of encoders, and then here, this is the output embedding, it is passed through a stack of decoders. Finally, you are producing the output, which is the softmax of all the bits. This is the at the output higher level. Okay. So what is the higher level mechanism? You are taking the input, embedding it, adding the positional encoding, passing through a series of encoders. Okay. And then giving it to the decoder. The decoder is passing through a series of decoders. Same process here, similar process. And then finally giving it to the softmax and producing which word is the next word for the language models. Not necessarily for the language models or the next word prediction. This can be, once you have the encoding, that can be used for any task. You can use it for classification, you can use it for speech generation, anything. Okay, depends on your task and time. Alright. Now, we'll see this one by one. When I talk about the embedding, what does that mean? I want to explain that. You are taking one hot encoding, multiplying it with a weight matrix, you get the embedding. Right? You get this embedding. Right? You get this embedding. You tell me, when you get this embedding, irrespective of the context, you get the same embedding for a word, right? 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 Suppose a mole is mole, M-O-L-E, mole. Okay? That has got a specific format and got when you multiply it with a word, I mean with a weight matrix, you get the same embedding. Right? For example, let's take three different methods. A mole on the right hand side. Mole has a different meaning. An American shoe mole, which is referring to an animal. Right? This has a different meaning. The mole is different meaning. One mole of carbon dioxide. This has a different meaning. Right? Right? Depending on the context, it is changing. Isn't it? Depending on the context, the meaning is changing. It means there should be somewhere that you impart the context information also into the embedding of that word, which the traditional models like LSTM, RGRU or RS did not fail. That's what we do in the attention mechanism. Alright. So we'll see step by step. We will start with this input embedding. So this is the tokenization. Whenever a text is given to you, we tokenize that text. Okay. So tokenization means what? Dividing that into some segments. Okay. So not necessarily space separated all the time. Although for our convenience, for the explanation, sometimes we give it like space separated words we take as the tokens. But in general, not necessarily that way. Okay, like teaching. In teaching, you can have teach as a one token, ink as another token. Right? Not necessarily based on the one word we go to, in general. But here in the explanation, we tokenize based on the words. Alright? So tokenize. Then, after that, after tokenization, when you are tokenizing, you also add some extra things like CLS class, SCP separation, and start of the character SOS. Some tags you put. Start of the sentence SOS, end of the sentence EOS. Okay, end of the text EOS. Like that, some tags also do it. Alright. Now there is some ID associated with each one of them. Basically, it is indicating the token ID. Okay, to generate the corresponding one-hot encoding, you need this. Alright. Now, this is this. One-hot encoding. This is the, so you see that it's a one-hot encoding of very big size. But you already know what is one-hot encoding, I did not have to explain. Alright. Only for one particular entity it is 1, rest of them it is 0, depending on. Suppose if the token number is 1, token ID is 1. Only for the first entry it is 1, rest of them it is 0. Token ID is 10. Then only for the 10th entry it is 1, rest of them it is 0. The token ID is 200, only 200 entry it is 1, rest of them it is 0. Alright. Now you transform that into the dense representation by multiplying it with the weight matrix. Any question? Okay. This is embedded. So this embedding, once you have this embedding, this can be visualized like a vector in the multi-dimensional space. Means each word is represented as a vector in the higher dimensional space. Generally, it is some, when you take ChatGPT, it is 12,228 dimensional embedding. 12,228 dimensional embedding. It means each vector, each word is a vector in the 12,228 dimensional space. Because we cannot visualize that much, here 3 dimensions I have shown. So these words are the vectors in those directions. Okay? So when you are capturing this embedding, you need to ensure that the semantic meaning is also captured. Okay? In a sense like, for example, I have the embedding for man, I have the embedding for woman. Okay? So the embedding for man here, embedding for the woman here, the difference should be able to capture the gender information. Okay? Similarly, if I take the corresponding nouns of king and queen, this direction should be able to capture royalty. That means, if I have the embeddings of men and women and queen, I can take the difference between woman and queen, which gives me the royalty encoding. If I add that to man, I should be able to produce corresponding noun phrase of the queen, I mean the male version of the queen, which is king. Okay? Similarly, some information, maybe the family relations we talk about. What is the, in the family relations, what is the man equivalent father? Female version of this is mother. Okay. So it means that difference we should be able to capture through these directions. Okay. It means certain direction is involving gender information, certain direction is involving royalty information, certain direction is involving something else. Understand? Understand? Right? Like for example, the gender embedding is one thing. Like for example, I want to describe French fries. French fries are so crispy and spicy. Okay? So the general fries embedding may be one direction. The moment you include crispy into the context, you should proceed in another direction that represents crispiness. Okay? If you include crunchy also, you should include another direction where it defines this information about the crunchiness. Understand? Right? That's how you can impart this information about the context into a word embedding. So that it represents the specific information about that word embedding in that particular context. In that particular context. Understanding, right? Alright. This is about the embedding. Now if you look at this architecture, going back, this is embedding. Once you get this embedding, you are adding positional encoding. Positional encoding. Okay. So far in the embedding, we have not included any contextual information. What I am saying is that we should include it. How to include is related. So far, irrespective of the position of the word, it gets the same embedding. Whether it is in the first position or the second position or third position, irrespective of the position, it gets the same embedding. Okay. To include the positional information, we have something called positional encoding. Positional encoding, which you see here. This is the input. Input is passed to the word. You get the word embedding here, and then to that you are adding positional encoding. Positional encoding. What is positional encoding? How do we add it? It means depending on whether it is in position 1 in the sentence, or position 2 or position 3, you are adding specific vector. How we take that vector, I will tell you. Don't worry. Right? We have the original embedding, plus we are getting the positional embedding. Both of them you are adding. That means, suppose it's the same word present in the first position, the same word present in the fifth position. Both of them will get a different embedding. Why? Because their positional embedding is different. Their original embedding is same, but you are adding positional embedding also to it. Because of that, the final embedding that you get after the positional embedding is different. Getting it? Okay. So that means so far you have given the sequence. Okay. Sequence of the words, let's suppose. Okay. The task is extra direction. So token 1, token 2 like that. Word 1, word 2, word 3, so on. Word n. For each one of them, you are generating an embedding vector. Embedding vector. Embedding vector. Embedding vector. Alright. So now you are taking the positional encoding and adding that to it. Positional encoding of the each word and adding. Same size. Okay, although because of the space restriction I reduce the size, but it's the same size. So you get another embedding here after that as a resultant. This is the embedding. E1, E2, so on, En. Understanding? So far is clear, right? Right. So let's see how the positional embedding is done. For the positional embedding, for example, if it is in position 1, I will be taking the values. This is a sequence of the curves with the different squiggles. This is a sine curve, cos curve, like that. Different squiggles with the different lengths. Alright. If it is in position 1, for the positional encoding, for example, I need 4 values, let's suppose. My dimensionality size is 4. Okay. So I will be taking, for position 0, I will be taking this one, this one, this one, and this one. I mean value here, and value here, and value here. Okay. Suppose if it is in position 1, so the position 1 on x-axis is here, so I will be taking this value, this value, this value, and this value. If the word is in position 3, I will be accessing to these curves, and I will be getting the corresponding values at position 3, which is indicated with the purple color here. If it is a position 4, then it is indicated with the blue color here. That means I am passing some values to this sequence of sine and cos curves based on their positions, and then getting the corresponding values and adding them to the original embeddings. Alright, so this is positional encoding. So once I get that, so you build a vocabulary. So assign numeric indices for each one of these vocabulary values. Alright. I mean, this is an example for a particular one. So consider trying a transformer to complete famous motivational quotes. So this is Albert Einstein's quote. Okay. He is given the part of the quote, you should be able to complete rest of the quote. That is the task. Okay. So first build a vocabulary. So this is the vocabulary of it. And then identify the corresponding indices. Once you get the indices, alright, represent with their embeddings. So this is word embeddings. And now you get the positional embedding also. So this is the input embedding. Different embeddings for the different words. Once you get the embedding, you also get the positional embedding. This is positional embedding of word 0, word 1, so on, word 30. So you have original embedding and the positional embedding. Original embedding and positional embedding. I hope you follow the same thing, whatever that I have explained. Are you looking? So far, right? So this is the final embedding. So this is word 0, word 1, word 2, so on, word 5 after adding. This is positional embedding, this is input embedding. Right? So the meaning of the word, so far, according to whatever we have seen, the meaning of the word sometimes depends on the context. For example, a more has different meanings here. A more on the right hand side, giving more attention to the right hand. And an American shoe pole, more here is giving more attention to the American shoe. Okay? And similarly, one mole of carbon dioxide, a mole here is giving more attention to the carbon dioxide. Right? So it means, depending on, see, when you read a paragraph also, suppose you read a paragraph, do you give attention to all the words? You will be focusing on whatever is important. Right? Suppose somebody give you a offer letter. What will you be focusing on? How much salary? Huh? How much? Do you give attention to all the things that they have read in the 2-3 paragraphs? No. Right? This one is salary first. Right? So the same thing. Right? Whenever you are reading a sentence or something, there are certain words you need to give more attention because they are more associated with this particular word, right? So that attention score needs to be identified to embed the contextual information. Okay, suppose if I have to embed contextual information on the mole, I have to give more emphasis to the right hand here, not a or on or the, right? Similarly, if I have to impart some contextual information, I have to give more attention to these words. Similarly here also. Okay, so how the attention scores are computed, let us try to understand that part. So in the self-attention, we are exploring this block. Okay, so in this block, so shall I make it short? Can I write these embeddings here now? Because you understood this process, right? Because I don't have space. Right? So you have the embedding which you have computed after adding the positional encoding. Okay? Positional encoding. Right? So you have embedding 1, embedding 2, so on, embedding n. Each one of these like vectors. Each one of them are like vectors. Right? Now, using which you will be computing three things: query, key, and values. What are these? Let us try to understand this intuitively. Alright? See, each one of these words asking information about the other words. How are you relevant to me? And trying to invite the other word information within this set. Okay? So this can be captured through three things: query, key, and values. Alright? Suppose there is a sentence saying that a fluffy blue creature is roaming in a verdant forest. Okay? Fluffy, blue are associated with the creature. Right? So now, if you want to update the creature may be some creature image. Right? Now you want to add fluffiness and blueness to this creature. It means some information about the fluffiness and blueness has to be added to the creature to make it a fluffy blue creature. Understanding? Right? So for that, this creature word is asking, hello, is there any adjective present in front of me so that I can add that information to me? Now this fluffiness and blueness are reacting to it. Yes, we are here. Okay, take the information from us. Okay, so this question that you are asking can be seen as a query, and the reply that you are getting can be seen as a key value. Understanding? So, if you have these words, you will be creating, imagine it this way, right? For each one of them, you are asking a query. You have the query 1, query 2, so on, query. Similarly, you also have the key values, key 1, key 2, so on, key n. I'll tell you how to generate the query and how to generate the key. Alright. So to generate the query, multiply this embedding with WQ. Okay, let the embedding size is some 1 by 100. Generally the chargeability is 12,288. Okay, and this query size is 120. It's GPT-3. Okay, so if you multiply this with 228 by 128. So 1 by 12228 multiplied by 12,228 by 128 producing 1 by 130. Okay, good. So for your understanding, let us suppose this is 1 by 1000. Now you are multiplying it with 1000 by 128, getting this query vector. So for each one of them, you are multiplying the embeddings with WQ, you are getting all these 1 by 128, so on, 1 by 130. These are the query vectors. These are the query vectors. Understanding? You have the embedding. Embedding is multiplied by what? WQ to get Q1, Q2, so on, Qn. Okay. Similarly, these embeddings are multiplied by WK to get P1, P2, so on, Kn. Okay. Now I want to understand how relevant is this Q1 to K1, Q1 to K2, and so on. So imagine These are like vectors in the 128 dimensional space. Okay. So let's take two dimensions because we cannot visualize that. Suppose if there is a key vector which is in this direction, if there is a key vector which is also in the same direction, what is that means? These two are similar to one another. If you take the dot product of them, you get the positive value. If they are in a different direction, you get the dot product, you get the negative value. If they are perpendicular to one another, you take the dot product, you get 0. So, when you multiply this key with the k values, q with the k values, it means you will be multiplying q1 k1, q1, q2 k1, and so on, qn k1, and so forth. This gives some values. If they are similar to one another, they are high positive values. If they are not similar to one another, then they are negative values. These similar negative values, if they are no relation, then 0. Understanding? Alright. So now you apply softmax on them. You get some entries, you get softmax on them for each column. That means which gives how much percentage of this key is responsible for this equation. Right? You take the softmax. Right? So I hope you find so far. What are you doing so far? Tell me. You taking the arithmetics, multiplying with WQ, getting Q's. Multiplying with WK, getting K1s. Now multiplying both of them, you get the matrix. This matrix is given to the softmax. Alright. Before that, we also normalized them by dividing with the size of the dimension, embedding dimension. I mean this dimension, equally values dimension. Right? Alright. So let me show you that. Right. So this is what. So you have this matrix which you multiply with this input. Okay, embedding. You get the corresponding query values. You have this embedding, multiply it with the WK to get the corresponding. Similarly for the values also. So this is what you get. Alright. These can be imagined like keys and these can be imagined like queries. Okay, these are the entries that you have got. Once you get that matrix multiplication, that's what we have done. Q multiplied by K. Alright, then what next is scaling? Scaling them is dividing by square root of dk. Alright, then comes, give it to the softmax. Softmax converts them into probabilities, which is basically attention. It means how much of attention I should pay to these keys. Other words, is decided by this attention. Alright. So this is how it is computed. For each one of the words, you have the query key values. Query key values. Query key values. Alright. So from each query, you are asking the other keys, how are you related to me, and taking the dot product. So for each query, you are multiplying with the corresponding keys divided by the square root of d. Alright, it is like this, right? You have the embeddings. The embeddings, after that, you have got these query values. Please see that. This is the problem. Please see that. So far you understood now. You have the embeddings. The embeddings are multiplied with WQ, you got all this. Right? And embeddings are multiplied with this, you got all this. You multiplying them, giving it to the softmax, you get the values in between 0 to 1. Now the entries are in between 0 to 1, all the entries. Alright, once you get this, what we do is that we multiply the same input, same embeddings with WB. We multiply the same embeddings with WB and get values, which are basically the linear transformation of the given embeddings. Alright, now these values are multiplied with the 0 1 we got here. Okay, please see. This is important thing. Once you understand this, I need not have to explain anything else. Okay, in the transformers. Alright? So cool. So far it is clear, right? in this entry, we got some 0.1, some 0.2, 0, 0.01, anything like that. What are these? Probability values. Alright, keep this like this. Okay, now you take the embedding, same embedding, multiply it with WD. Multiply it with what? WD. Okay, like that you will get V1, V2, so on Vn. These are value vectors. So far you have Q vector, query vectors, key vectors. Now you got value vectors also. Okay. Now you take this each value vector, multiply it. Okay, that's what is done then. Right? Multiply it with value vectors. Right? So it means multiply this with V1, multiply this with V2, and so on, multiply this with Vn. Okay, so now I want to update the embedding. So far, what I have done is that how much attention I should pay to the other words. That's what I want to find out. Okay, it means how much of the information from the other vectors I should take and combine it with me. This is what is asked, right? So you are taking the value and the corresponding attention, taking the multiplication from every word. Okay, so suppose if I want to update the embedding of this word, okay, so you take the value which I have to take from this word, so on this word, take the summation over all of them. This gives how much of the information I should take from the other vectors. Understand it? This means you are computing the value vectors, multiplying them with the corresponding attention score, taking the summation over all these attention scores multiplied by their embeddings or values. Okay, that is change that I want to apply, that I want to add to the current vector. So you compute the change over each and every column after the original embedding. Understand it? Right? So, to tell the process mechanically, we have the embeddings which we have created. Alright? Using this, multiply this embedding with WK, you get the key values. Multiply this embedding with WQ, you get the Qs. Multiply Qs and queries and keys. Okay? You get some entries. Give it to softmax. You get 0 to 1 values, which gives you attention. Keep that aside. Alright? Now you take the embeddings again, multiply them with WD, you get the values. Multiply them with the corresponding attention scores. Right? So how much attention I should give to the other values given by these scores? Take the summation over all of them, add to the current embedding. Summation over all of them and add to the current embedding. I think the process is clear. Right? So this is the updated embedding. Okay? This is what self-attention does. Self-attention mechanism is this. Okay? So through this way, what are you doing? You are imparting the contextual information from the other vectors, okay, other words in the sentence. If you do this one time, it's not sufficient. Okay? What we do is that we do is repeatedly. We take the embeddings, perform this attention, then linear transformation, then attention, then linear transformation, then attention, like that. Repeatedly we do the process. Okay? So at the end, it imparts so much information from the other contextual parameters. Understand me? That means even the end word also able to capture the entire context of this paragraph. Therefore, using the end word embedding, give it to the softmax. Okay, so at the end of this story, after so many such repetitions, what will you have? You will have the updated embeddings. Right? So you have the embedding here. This information is flown from one vector to the other vector like this. After so many such iterations, this is able to have the entire contextual information. Right? So let's suppose this is some 1 by 1000. Okay, now I have in my vocabulary 10,000 words are there. I want to predict what is the next word. What I do? This 1 by 1000 I will take, multiply it with 1000 by 10,000, 1000 by 10,000, which will give me 1 by 10,000. This is passed to the softmax. Softmax. This gives the probability distribution of the 10,000 words. And I pick up the word that maximizes the probability. I pick up the word that maximizes the probability. Alright. Now, once I generate this next word, to generate the next word, what I do? I take some input, generate the next word. I include the generated word in this. I repeat the process. Generate the next word. Include that in the text. Generate the next word. Include that in the text. Give it to this. This is how repeatedly I pass it to the GPT and then generate the next word, and so on. Got it? Right? So depending on the task, you have different things here. In the transformer, we have the decoder also, which is basically used for the language translation. That is basically used for the language translation. That is basically used for the language translation. Alright, let us see the details of it. So this is what is happening. And if you notice this, original architecture, I don't know whether you are able to see it clearly or not. But this is multi-head attention. What we have noticed so far is a single head attention. What is multi-head attention then? In single head attention, what are you getting? The change that you need to add from the other vectors and adding to the current embedding. Okay, this is one aspect, one attention. Okay, multiple such attention blocks will bring the multiple aspects. It means you will be simultaneously applying multiple such attention blocks. So complex blocks are, but try to understand. One attention block you understood is producing one change that you are adding to this. Like that you are apply the same process simultaneously. Okay, in ChatGPT we have 96 attention heads. It means 96 self-attention blocks are working simultaneously, producing 96 different changes that are to be added to the original embedding. Okay, that means the updated embedding is original embedding plus the change over all these 96 heads. Understand? Right? So you get the final embedding. Right? So this is multi-head attention. And then linear layer, which is basically giving the transformations. So the encoder network, I hope you understood what is happening inside the encoder network. Okay. Shall we review it one more time? You have the original embeddings of the words, and then you are taking the positional embeddings, adding it. You are getting some embeddings. Now you are giving it to the self-attention network, which is taking the contextual information and transferring the knowledge to the other words. Okay, imbibing the information from the other words. Right? Like this, you understanding how much information I should imply from the other one and adding that change to the current embedding. Like this, you are doing for multiple attentions parallelly, adding all those changes to get this updation. Then, once you get the updated embeddings, you are doing linear transformation on it, and then self-attention, and then linear transformation, and then self-attention. So this entire thing is called, each one of these linear attention thing together called, parallelization together called one encoder. Like that you have stack of encoders. Okay. At the end you get the final embedding of the encoder network. So this encoder network is nothing but a stack of encoders. Each one of them has a sequence of operations. Okay. Attention, linear, normalization. Like that you have the sequence of encoders, stack of encoders, and at the end you will get the final embedding. This is encoder network. Alright, now let us try to understand the decoder network. By the way, this particular thing that I am describing is for the language translation. Machine translation. What is machine translation? That is taking text from one language and transforming that to another language. Okay. So the encoder is taking all this text and encoding it into factorized format. Now the decoder has to transform that into another language. Okay. So initially we pass start of the sentence as an input to the decoder. Start of the sentence as an input to the decoder. So for the decoder network, we pass one word at a time. Initially start of the sentence. We generate the first word. Okay. Then include that in the end. Now you have start of sentence and the first word. Generate the next word. Now next time, start of the sentence, first two words. Give it to the decoder. It generates the next word. Now three words. Generates the fourth word. Four words. Generates the fifth word. Five words. Generates the sixth word and so on. Finally, it also generates end of the sentence. Then you stop. Clear? Right. Now how it does this? The same process is almost repeated here also. But here we use mass attention. Mass attention. Mass self-attention. What is mass self-attention? Okay. So many things. Okay. Try the focus. Mass self-attention. Alright. So you see this. Do you remember this key query values table that I have plotted earlier? Remember? Right. So these are the queries. Okay. I think in the slides I have taken rows as the queries. Okay, don't get them. Alright. So queries and these are the keys. Alright. So when the decoder, when you are in the very beginning, you have no information about the later words. So you don't want the later words to influence the present query. Isn't it? So initially, when you are at this stage, you have only the first word known, right? That means the complete distribution or the attention should be limited to this. All this should be zeros. Similarly, when you are at second stage, the probability distribution must spread across these two. All this should be zeros. Right? And similarly, when you are at the third iteration, the complete attention should belong to these three. All this must be zeros. Answer. These are queries, right? Yeah. So here, this should be 1, all this should be zeros. And here, we should be distributed across these two, and all this should be zeros. And this should be distributed across these three, and all this should be zeros. 4. Sorry. All this should be zeros. Okay, that means when you are computing these key query values, what you do is that you get some value. You take the upper diagonal, keep the values as it is. Take the lower diagonal and put them to minus infinity. Put them to minus infinity. So that when you give it to the softmax, this minus infinity, 1 by 1 plus e to the power minus infinity. No, e to the power minus infinity divided by this. Alright, this becomes actually zeros. When you give it to the softmax, this becomes zeros. This is called masked attention. So you are masking the inputs so that certain entries will become zeros. So you don't want the later words to influence the current word. Okay, that's the reason why you do this. Right? This is masked attention. Let me show you that. in this particular example, queries are given as the rows, keys are as the columns. That's why in the upper diagonal we fill with minus sign. So that after taking softmax, all of them will become zeros. Alright, it means the attention scores at this stage are only limited to this, attention scores here only limited to these 2, these 3, these 4, these 5, etc. This is what I am talking about. Mask multi-head attention, which is the decoder. This is also the same. You take the original embedding, positional embedding, take the summation over. After that, instead of self-attention, you apply mask to self-attention. That's the only difference. Okay? So it means half of the diagonal, you are making minus infinity forcefully. That's the only difference from self-attention to the mask self-attention. Alright? It means after you compute query matrix times transposable key matrix, you get some scores. In this score matrix, you build this upper diagonal to be minus 2, so that you get zeros. Alright. This is the transformer illustration. You have the original tokens. So original embeddings, you are taking or involving information from other vectors and updating them at every stage. Once you are done with the encoding process, now you have a decoder. In the decoder, you are starting with the start token, and then you are taking the information from the other tokens, also from the decoding network. It means your decoder, it means the encoder embeddings are also acting like keys for the decoder. This is called cross-attention mechanism. Okay. So far, if you look at this self-attention mechanism, queries are also from the input, keys are also from the input embeddings. Okay. But in case of the decoder, suppose I don't know. You want to translate that to Hindi. मुझे पता नहीं. Okay. This is the translation. Initially you start with start of the sentence. Okay. Then मुझे पता. मुझे पता नहीं. Right? That means when you are generating मुझे, you are taking the information from the start of the sentence and also I don't know. That means your keys are not just मुझे. Your keys are मुझे and I don't know also. Similarly, when you are generating मुझे पता, right? Your keys are मुझे पता and I don't know. When you are generating नहीं, your keys are मुझे पता नहीं, I don't know. It means the keys, the information you are also taking from the source language. Okay, that means the embeddings of the source language that you have in the encoder. Okay, in the decoder process, one step at a time, you are taking the information. So see that, that's what is happening. Means iteratively it is happening, not all at a time. Okay, so initially you are starting with the original embeddings and preserving the contextual information by interacting with the other words, updating the embeddings, and then repeating the process for few encodes. Then once you have this final encodings, you are starting with the start of the sentence, then taking that information from those keys and updating it. Now you have the second one, taking the information from this one as well as this one and updating them. Now you have third one, taking the information from these ones and those ones also, updating it. Now you have fourth one, taking the information from these ones and those ones also, updating it. Okay, so this is decoder. The stack of such decoders will produce you the final embedding, using which we will be generating the word, next word, in the destination language or the target language. Okay. So, although we discussed it for the machine translation, this can be applied for any other task also. Okay. So imagine it's an image to caption. Okay. For images also you can apply self-attention. How do you apply? How do you apply? Achha, I will not go to the details of this now because we don't have much time. But once you understand the transformer, it is very easy to understand BERT and ZPT because the BERT is the only encoder model. It means this part part it is taking. GPT is only decoder model. This part only it is taking. Okay. So this is some representative architectures, but original architecture slightly deviates depending on the application. If time permits, I will come back to this GPT-3 and all, but let me show you something. This is image caption generation with attention mechanism. Okay, so please observe, this is the image. Now you apply CNN. Once you apply CNN, what will happen? CNN, yesterday we discussed it, right? Series of convolutional Rayleigh pooling. Finally, what you get? You get an image with a number of channels, right? That means each pixel here is represented on a t-dimensional space over the number of channels, right? Like this. Understand? So you have an image convoluted with a number of channels in it. Okay. If you see the depth, this is description of this one over the number of dimensions. Understand it? Like this. If I have an image, like 3D image kind of thing. So this one is one vector. This is another vector. This is another vector. Like that, I have multiple vectors like. Hello? Understand it? Or the depth if you see. Right? So you take each one of those vectors. Treat them like word scale. And apply self-attach. Understood? Here also you are embeddings only, right? Then they take each pixel embed after the convolution. Right? Apply self-attach. Generate key values, generate query values, multiply them, normalize them, softmax them, then multiply it with values, you get the attention scores. Okay, once you get the attention scores, you see that how much of information you extract from the other entries and add to the current pixels. Update it. Okay. Now you pass that to the decoder. You see that this is what is happening. This is after convolution. Now you are finding out the attention scores. Alright. You multiply them, getting the attention scores. Right? These attention scores are multiplied, you get the context vector. It means the entire context of the image is represented in this vector. Now you pass it to the RNN kind of network, there is a sequence of words as the captions. Sequence of words as the captions. Alright? That's what it is doing. Right? You see this. You take the context vector and also the output of this, generate the output. Okay? A. Word. So generating the caption as a bird. Do this. Right? So the attention is applied on the image here, which is translated or given to the sequence decoder and generating the text a bird. Right? Similarly this one. This is language translation. Here also you apply attention, you get the scores. Okay? Once you get, you compute the cross attention, find out the contextual representation of that, Once you have that, represent the entire context using the C1. Now make use of this to generate new language. मुझे पता नहीं. End of the sentence. Okay, like that. Once you have an idea about this, how to encode the information, that encoded information can be used for any task. Whether it is a language translation or a question answering or summarization or text classification, anything. Only the last few layers will change. Isn't it? So once you have the encoded information, you use it however the way that you want. Understand? Right? Clear? So GPT-3 also the same thing. Only thing is that there you only use the decoder. It means, let me tell you this. GPT-3, you are asking some question. You are asking some question. These models are pre-trained on a huge volumes of data, Wikipedia, this, that, lot of sources. Okay, for the next word prediction, PC. They are trained for the next word prediction. The simple difference, let me tell you, between word and the GPT. Okay. You have unsupervised learning. initially on the decoder stack of the model, which is the second part of the transformer. Alright, we'll be training them for the next word prediction on a huge volumes of library. You cannot imagine that. Okay, that's those many huge volumes of library. What they are trying for? The objective of the next word prediction is the objective of the. Once you try them, specifically if you have some tasks, you can rewrite them in a small data set, otherwise leave it. Alright. Now a query is posed to the GPT. Okay, where is tell me something about Narayana Engineering College. Okay, so take this as the pretext for your answer generation. Take this as the pretext for the answer generation. It means all these tokens plus start of this sentence. Right? Now it will generate the first word in the answer. Include that. It will generate second. Include both of them. Third. Include that. It will generate fourth. Like that. It's not a word actually, it's a token. Technically speaking, it's a token. Generates next token, next token, next token. Understood how it works? The same. Once you understand the transformer, it's the same. But coming to birth, we use only encoded one. The encoded part of this. Okay. We also pre-train using unsupervised learning. But we pre-train them for the missing word prediction. The word in the bidirectional. Okay. Bidirectional encoder representation or something. Word abbreviation. Okay. Like your trial is here. This is also works in bidirectional. But with the attention mechanism. Alright. So it means you have given some paragraph in which you will be masking off some of the words. It means you are filling them with some empties. Dash. You have to fill in those dash. Right? So now you will be looking them from the front, you will be looking them from the back also. Generating or predicting the missing words. Predicting the missing words. That means the objective of the network is to rightly predict the missing words. Once this training is done, then you give it to any task like text classification or anything like that. Okay? So take a small data set, retrain it on the text classification and perform. Only the last few layers will change. Once you have the encoded information now, you just add some linear layers, right? Or fully connected layers and then perform it. Alright? I hope that's clear? Right. So, to conclude, in today's class, we discussed sequence modeling, in which we started with recurrent neural network, in which we discussed single RNN cell, which is taking input, current input, and the input from the hidden, taking some function of it, and then giving the next hidden. And this process is repeated over different time steps. Alright? And then we see that some disadvantage of this, which is vanishing gradient problem. Okay, to address this, we have seen two solutions, LSTM and ZRU cells. Okay, it means a simple computation of RNN cell is replaced with a gating mechanism. In LSTM, there are three gates. Can you tell me the three gates? Input gate, target gate, and output gate. Okay, there are three gates. Alright, each one of them is trying to see how much of the previous information to be passed or discarded, how much of the current information to be passed or discarded, and how to update the next level, short-term and the long-term memories. Right? In GRU, so in LSTM, it is taking 3 inputs and giving 2 outputs. In GRU, it is taking 2 inputs and giving 1 output. And there are 2 gates in the GRU cell. One is forget gate, update gate, and reset gates. Okay, thanks. Alright. Then this is also based on the same concept. How much of the previous information to be forgotten or discarded or carried forwarded. Right? Then we said that somehow we are missing the contextual information in all these cases. Okay? So we have something called self-attention mechanism. This is the self-attention mechanism, a transformer concept in which we are internally using self-attention mechanism. So the transformer is taking the input and then taking the embedding of it. It is taking the positional encoding, adding this embedding plus positional encoding. right? Once you get this embedding, it is generating three values: query vector, key vector, and value vector. Queries and keys are multiplied and normalized and given to the softmax to get the attention scores. And these attention scores are multiplied with the values and take the summation over, which gives the information that how much of the information to be extracted or imbibed from the other vectors. Add that change to the original embedding. Add that change to the original embedding. So this is single head attention. If you have multiple such heads or attention blocks, we call it as a multi-head attention. Each one of them producing the change to be added to the original embedding. So if I have 100 such self-attentions, I'll be adding 100 changes to the original embedding. Right? Once you get that embedding, you pass it to the fully connected layer, then attention, then fully connected, then attention. We're calling them as sequence of encoders or encoder stack. Okay? So once you get all this information, the final information is encoded in the final embedding vectors. Right? Now if you want to decode it, start with the start of the sentence and then repeat the process. Apply masked attention and then use this attention together with the embedding vectors in the encoder and generate the next bit. Now you take both the bits together with the original embedding vectors, generate the third bit, fourth bit, fifth bit, and so on. Okay, this is for the language translation task. Okay, if you have only encoded or only decoded models, those are also there, like BERT is an example of only encoder, GPT is an example of only decoder. Initially, we will be planning them for different tasks, and then later we will be using them for some other things. Okay, for example, BERT is kind for filling the gaps, kind of like mass word prediction, and later it can be used for any other task like fine-tuning it. Alright. Similarly, the GPT-3 is trying for the next word prediction. Alright. And then we pass the query as the prefix to the initial prompt, and then we generate the first word, second word by iteratively applying the same process. Right? Clear? Alright. If you have any questions, I can take. Otherwise, that's all from my side. Thank you very much. I hope you pick something out of this. Alright. I can take questions. Questions or interaction? I have time. 10 more minutes. So, if you have any question and you want to interact, ask any kind of other general things, anything. Understood something at least some 50%. Alright, thank you guys.